Okay, so how about for completeness for anyone watching the recordings, the 10-second summary is if you go to dedalus-school.org and click on Notebook 2, we're going through the end of Notebook 2. All right. Oh, there we go. Okay, so we've talked about representing variables and doing operators. So, okay, on to PDEs. So, okay, any PDE we want, we have to put into this form. So for this notebook, we're going to look at the 1D Burgers and KDV equations. So the 1D Burger equation, which I think came up yesterday too, and maybe last week a bit too, you know, it's a nice model problem of Navier-Stokes, so it gives us 1D advection and diffusion, and it actually forms shocks. So we said before that the spectral method is not good if we have shocks, but we're going to forge ahead anyways. And you can think, okay, maybe what should we expect to happen when the shock forms in the solution to this problem? So we'll see that in a second. But this is the equation. So just first derivative of u, and then this advective term u dot grad u in one dimension is just u times dx of u equals a times second derivative. So this is a diffusive term in 1D. Okay, so this is the viscous Burgers equation. So how do we do that? Well, we want to say we have this parameter for the diffusivity A. Let's pick 2 times 10⁻³ and then we make an initial value problem, and the variable we want to solve for is u, and then there's this funny little thing you have to do. So this is sort of a hack if you know Python. So locals here, this is basically the dictionary of all variables in a script. So if I pass this, then when I type in the equations, I can use any variables I've defined anywhere in my script, and Dedalus will understand them. So like here, this will say, okay, A can come from here, and U is the field I defined, and then the DT and the DX are built in, so it understands those. Okay, so what do? We create the initial value problem, then we just add the PDE, and it's just this equation, but rearranged into this form. So the linear terms have to be on the left, so we move over the diffusive term to the left, and the nonlinear terms have to be on the right, so we move the advection term over to the right. Yeah.
Is there somewhere that lists like all of the operators, like dx or dt or?
Yeah, the best way is basically to go through the example scripts or the tutorial notebooks. So on the website, so let's see, if you go to dedalusproject.org and go to the documentation, then you can go to tutorials and examples. So there are 4 tutorial notebooks here, which are they're more thorough versions of what I'm going through now. So they really document all the different options for all these things. And then there's also a bunch of example scripts for problems in different geometries and with different kinds of physics that you can work from also. So usually the easiest thing is to like find the closest example to what you want to do and modify it from there.
But like, is there somewhere easy in the Python code that tells me that, like, say a derivative is lowercase d, maybe I wanted capital D if I was looking at Lagrangian equations or something?
Yeah, those are kind of spread in different places in the code, but the notebook, I think, enumerates them all, so that's probably the easiest place to find it. Yeah, cool. Okay, so, all right, so there we go. So just as like an aside, so this is, I don't know, maybe an unfortunate part of Dedalus that the equations have to be this way, linear on the left, nonlinear on the right, because we always for fluids want to solve equations that kind of look like this, right? They have a u dot grad something on the left, and they have a diffusion on the right. So in your Dedalus script, those things should basically always have negative signs, right? And if not, it probably means you made a sign error moving terms back and forth. And if you put a sign error here, then you're going to have anti-diffusion and things will explode. And this is still a mistake I make like every month when I write a new Dedalus script. So that's definitely something to look out for. Diffusion should be negative on the left-hand side of the equation. Okay, so when we execute this, nothing happens, right? This is now just creating an object that represents the system of PDEs. It's not actually solving anything. So the solver class is the thing that actually solves this. So again, this represents a PDE in space and time. So to discretize it and integrate it forward, we have to specify a time stepping scheme. So again, Dedalus has this a library of different time stepping schemes. There are different Runge-Kutta and multi-step schemes if you're into time steppers, so you can look at the list of implemented ones. But usually we just try a few and see what works well for a given problem. And once we select that, we can then pass that to this build solver method and get an object that's actually the numerical solver for our system. Okay, so you see when we did that, it printed out this thing at us. It said building subproblem matrices 1 of 1. So this is actually where it's doing the step of constructing the discrete L matrix by doing this projection of our operator against our test and trial functions, right? So when we made the problem object, that's kind of saying what L is, right? What's the PDE? And then the solver is actually making the discrete form and like actually calculates the matrices that then we'll solve later on. Okay, so this can be a slow step if you're doing a huge problem or it has dense matrices or something like that. But then that's just a startup step. And once we do that, we can evolve the solution. So there's a few different stopping criteria. Here we're going to say we want the solver to stop after 10 units in simulation time. You can also tell it to run for a set number of iterations or a set amount of real world time. There's a few different conditions like that. Okay. So then we need to set the initial conditions, right? What we want the starting state to be. And to do this, we just directly set the values of this U field, right? That we want to evolve with the problem in the solver. So here I'm just going to set it to this initial condition. Doesn't really matter what it is. This is like a triangle. So under Berger's equation, we expect this to sort of like tilt over and form a shock and then travel towards the right. Okay, so we've described the problem, set up the initial conditions, and now the main thing that's left to do is just to run the integration. And sort of a unique thing about Dedalus is that the main loop for the integration is directly in your simulation script. So here, this is a main loop that I've written that's going to just iterate at a fixed time step and periodically save copies of the solution. So I've picked a time step, and then I'm creating lists where I'm going to save the simulation time and the solution at different times. So I just copy the grid values to this list. And then here's the main loop. So we say while solver.proceed. So what this will do is that'll execute to true until we hit the stopping criteria that we set above. So until we get to a simulation stop time of 10 units, this loop will be true and keep evaluating itself. So then we tell it to take a time step of the size that we specify, and then we can like print things out periodically, and then also periodically save the solution state to these lists. So Dedalus does have like a more comprehensive output system for saving to disk, but just for this simple example, we're just going to save the solution by making lists of the values. Okay, so if we run this, then it'll print, and it just did it. Okay, so it just evaluated 5,000 iterations. So again, every 500 iterations, it gives us this printout of the simulation time and the time step, and then it went through. And then at the end, when we hit the stop time, then this while loop broke, and it tells us that the stop time was reached. Okay, so now we have lists of the solution in space and time. So we can just do a p-color mesh plot to look at the solution in space and time. Okay, and here we go. So this is space on the x-axis, time on the y-axis here. So our initial condition was this triangle centered at t is 2. And as time goes on, that sort of tilted over until it formed a shock around here at t equals 1. And then from that point on, the shock sort of moved over slowly to the right, and its velocity kind of slowed down as it went, and the amplitude sort of dissipated. Okay, so this is the solution we expect for a viscous shock. And on the one hand, it kind of looks like there's a big jump here, right? And I said spectral methods are not good if you have discontinuous solutions. But the key here is that we have viscosity in the PDE, right? We added an explicit diffusion term So the shock is not going to be infinitely thin. It's actually always going to be rolled off and regularized by the viscosity that we put in the model. And as long as the viscosity is big enough such that that roll off is resolved by the grid or by the Fourier modes that we include, then we'll get a good solution. Because mathematically, at the scale of the smallest Fourier mode we have, the solution does look smooth if that's smaller than this scale. And so the resolution and viscosity here were carefully chosen such that that was the case. And we can look at that by zooming in onto the shock at some time. And we see that this is actually what it looks like. So we sort of have enough grid points. And again, this is a proxy for Fourier modes because the highest mode sort of oscillates pi radians per these grid point spacings. So we have enough grid points to actually resolve the shock, right? This is not a jump where we go from one point straight to another. We have like 4, 5, 6 points across the shock here. Okay, so this is sort of the key, right? Oh, yeah.
Yeah, hi. So trying to wrap my head around what's being stored on so we go up to where you're copying the array to store for later printing.
Yeah.
We're copying np.copy UG, right? Okay. And that UG is already the sampling grid of the function, right?
Yeah.
Okay, so the question I'm trying to get at is, once you set what the grid resolution is at the beginning, and you're evolving these continuous functions, you can't change that grid resolution at any point. So you're kind of stuck with whatever you start with.
Yeah, that's right. So
okay,
yeah, it's a good point. So sort of the characteristics of spectral methods in general is that they're roughly equi-resolution. That's not quite true. They actually, when you use Chebyshev, you get better resolution near the boundaries, like the Chebyshev modes oscillate more quickly near the boundaries. So they resolve boundary layers well, but really in the interior, these are roughly equi-resolution schemes, and they're also like static resolution schemes. So this is pretty far from, either static mesh refinement or adaptive mesh refinement, right? So these methods tend to be good for like if you have a box full of turbulence and you need roughly the same fine resolution everywhere, then this is very efficient. But again, if you're in the regime where you have like shocks and only have small features in some parts of the domain, even if those are regulated by small scale viscosity, you're still potentially like using more degrees of freedom than you would really need if you had an AMR code or something. Yeah. Yeah.
Maybe I'll just add that the simulations I showed this morning, in that case, we had a lot of resolution in the convection zone. And in that region, your resolution requirements are homogeneous and isotropic. Then when you have the waves, you need much lower resolution to capture the waves. So actually using this, using kind of two bases and kind of gluing them together at the interface with a ball in the middle of the shell on the outside, that's a nice way. So that's kind of like some sort of very rudimentary static mesh refinement. It's like spectral element perspective. So so in that case, like I knew a priori that I only needed high resolution in a certain spot, not in other places. So you can do things a little bit like that, but where things are moving, where you need the high resolution over the course of the simulation, that's not, like these types of methods are not necessarily good for that.
Cool. Okay. So all right, so that's the simulation. That's the viscous shock. And then I guess, right, really the power of this system is the flexibility, right? So here we simulated a shock that was regularized by viscosity, but say we want to put in different physics, right? And instead of like a viscous term, say we had a dispersive term. So instead of second derivative, we want a third derivative for this linear term. So this is called the KdV equation now, or Berger's KdV. And the idea is that we can take all the same code from above. So here I've just copied each of the cells from above, and everything's exactly the same, except I've defined a parameter b, and then just changed this term. So instead of a times the second derivative, we just put b times the third derivative. and we can execute the code again, and it runs, and now we can plot the solution there. Okay, and we get this. So it's totally different, but this is what happens when you have a shock that's regularized by dispersion instead of by viscosity. Now, as soon as the shock forms, you get these like oscillations emanating from the shock front. And you know, again, this is just a toy problem. Like here, it's periodic, so that actually like wraps around back into the solution later on. But again, it's just an illustration of, you know, the point of the system is really the flexibility on the modeling side. Okay. Any questions on the 1D setup and examples? Yeah.
I guess just related to the limitations of the code, like, are there any specific like science applications you could think of where you, at least at this point, you wouldn't want to try to represent using Dedalus as far as it seems to be handling the shock somewhat okay.
So this is a case where, you know, we've intentionally put in a large enough viscosity such that we know it's going to be regularized, right? So that's much higher than what the viscosity would be in a physical system, right? So I think in general, that's the way to think of these is the spectral methods, right? They give you very accurate numerical answers when the PDE has smooth solutions. So there's sort of a trade-off, right? We're almost never simulating a fluid system with realistic microphysics and dissipation. Instead, we're artificially increasing those enough to the point where we can resolve a smooth solution on our grid. And then we solve that problem with very little numerical error. So in general, you're trading off model error for numerical error, right? We're making large model errors, but then doing that, we can solve the resulting PDE very accurately. And then we can see how far we can push the model parameters. And we don't really need to be worried about numerical effects because we're always in this regime of like high convergence. So it's just sort of a different approach. You know, this tends to be something you see more in kind of the fundamental fluids literature, also the geophysical fluid dynamics literature. I'd say historically, parts of astrophysics are sort of the other way, right? They put in as many physical ingredients as they can, and then you just know that you can't resolve all that. So you put in some sort of like grid scale dissipation or subgrid modeling to take care of the numerical issues. And neither approach is perfect, but I think they're kind of complementary. And I think this one works well, like in these cases where you have simple geometries and relatively simple physics, maybe. Yeah. I don't know. Anything to add to that?
I think spectral methods are useful in terms of things for astrophysics, where you have, in terms of fluid dynamics for low Mach numbers, where you don't get shocks. I mean, we have run simulations with, like say, convection, which is high Mach number, and you form shocks, and it's completely fine. The shocks seem to be propagating exactly how you expect. But when things are very high Mach number and everything's done by shocks, I don't think that this is probably the most efficient numerical technique. And then the other thing is exactly what we were discussing before, the homogeneity. These are really good if kind of the action's always going on in a distributed area that you know beforehand and which has a simple geometry. If you're doing like a galaxy formation simulation, in that case, you want to have a lot more resolution in the galaxy than outside the galaxy. So this is not going to be very good for that. So like homogeneous systems and low Mach number flows, I think are good use cases.
Yeah.
When exactly did we set the basis we were using / the boundary conditions we were using?
Yeah, good question. Okay, so the basis was set kind of all the way up here at the beginning. So if we go back before the problem, before the calculator, okay. So all the way up here. So we made, yeah, the coordinates in the distributor, and then here, yeah, this is where I picked Fourier basis. And then it's a good observation. So the example that we do after this, maybe after we take a little break, is going to involve boundary conditions. So the Fourier basis and spherical harmonics are sort of special cases because those don't have boundary conditions. Those bases imply periodicity in some sense, right? So when you say Fourier, this is, all the variables here will be periodic. So you don't need to add that as an extra equation that's enforced at the basis level. And same thing on the surface of the sphere. So in spherical harmonics, there are no boundaries, right? Just like moving on the surface. But then if you have Chebyshev, so you want to do a box or like a ball or a shell with radial boundaries, then we'll see that you have to add in some extra terms and also add equations to specify those boundary conditions. Yeah.
I think in principle, you can also play with the coordinate system, right? So,
Uh-oh,
is that working?
I broke something. Oh, okay, sorry. Yeah.
If you want to resolve some region in space, you can pick a coordinate system that's.
Yeah, that's right. I mean, there are lots of like, what we said were sort of the general cases. You can definitely make like stretched coordinate systems or things that like, resolve certain areas more than others. And you can include those things in terms in the PDE. That's possible. But I'd say that works well if you have sort of like moderate distortions of your domain. The more and more extreme you make those distortions, what actually ends up happening in a lot of cases is that the spectral representation for those variables will no longer converge exponentially, because your remapping is sort of going to introduce, you can think of it in terms of complex analysis, you're introducing maybe poles in the complex plane that correspond to this coordinate transformation, and that technically ends up limiting the convergence rate here. So you're right, and that is a very good technique for moderate distortions, but you can only push that so far before you lose accuracy. Cool. Okay, so that's the first notebook. So just the basic API and the different sets of objects we use, right? Bases, fields, operators, problems, solvers. Like I said, we're going to pretty much skip the next two tutorials that you would find on this website. Maybe I'll say a few words about them real quick, just in preparation for skipping to the last one. So that was a 1D periodic problem. Okay, that's sort of the easiest thing we can do. Next up, the lecture 3 notebook here is 2D periodic with forcing. So this is a 2D turbulence example. And I'm not going to go through it all in detail, but I'll just point out the main things that it's adding. And then I think Daniel will cover these in a bit more detail with the last example. Okay, so now this is a 2D problem. So we make two bases, or we have two coordinates, Cartesian coordinates in x and y, two Fourier bases for x and y. And then our variables, if we want them to depend on x and y, they get both of those basis objects. Okay, then in multiple dimensions, we can also use vector calculus, right? We don't just have a partial derivative. We can use a Laplacian operator, a gradient operator, and so on to simplify the multidimensional calculus. This example also spends a lot of time explaining how to do stochastic forcing. I'm just going to skip over that, but you can read it if you're interested. But then this is 2D incompressible hydrodynamics in the stream function vorticity formulation, again entered in terms of these like vectorial operators like Laplacian and gradient. Okay, I think the other thing that this notebook shows that the first one skipped was how to do output instead of just saving lists in the main loop, right? That works well for a 1D problem, but really to do bigger problems, you want to use what we call the evaluator framework. And this is a way to create and save data to HDF5 files as the simulation runs. And it uses sort of the same symbolic framework as the equation entry. So you can create operator trees that represent certain operations and then save those things using this sort of syntax here. Again, I won't go into the details, but this is really the right way to do outputs as you run. And it's very easy to customize what types of statistics you want to save or what types of things you want to calculate along the way. And then finally, the first example, we just did a fixed time step, but often with hydro simulations, you want to do adaptive time stepping based off of a CFL criterion. And there's also a simple object to do that. So this is called CFL, and then you just give it the velocity vector. And so now in the main loop, every iteration, this thing will compute a time step based off of the CFL criterion on the grid using the velocity, and then automatically adapt the time step. So now the main loop kind of looks like this. We still have like a while solver.proceed, but then we calculate the time step from the CFL criterion. Here we're setting forcing for the stochastic forcing, but don't worry about that. So then now we still take a step, but we're using the adaptively chosen time step here, and we don't have the saving lines anymore because we made those file handlers for saving to disk, so we no longer have to do the copies. So this is much more of like what a regular main loop will look like in a Dedalus simulation. Okay, and then I think this script also includes some post-processing things like how to load the data, plot snapshots, plot power spectra, that sort of thing. And then I'll just play the video at the end. So here's a video of the power spectrum of this problem. So it's 2D turbulence forced at some wave number, and then you develop a forward and inverse turbulent cascades over time. Okay, so that's notebook 3. And then super quickly for notebook 4, this doesn't really introduce too many new concepts except for different types of problems. So far we've been looking at initial value problems, but a really powerful part of Dedalus is to combine the boundary value solver, the eigenvalue solver, and the initial value solver. So what this notebook goes through is those 3 steps for a particular problem from geophysical fluid dynamics, where you use the boundary value solver to solve for some background state. You could think of it as like an atmosphere profile. You use the eigenvalue solver to find the most unstable mode on that background state. And then you use that to set the initial condition for the initial value solver. So you can sort of evolve the most linearly unstable mode in your problem. I'm not going to go through the details. I'll just play the movie at the end. So here, what we actually solve for is the boundary value solver is solving for the profile of a jet. So this is a problem on the surface of a sphere. And there's a jet, so just a band of flow moving around the pole that way. So we solve for the structure of that. We find the most unstable mode, and then we seed that most unstable mode, which is the perturbation that you see growing here, and it makes this set of vortices around the jet. Okay, so this is just a very useful way to sort of initialize with good modes for your time evolution problems. Okay, so I think I'll cut it off there, and maybe we should take a break for 5 minutes or so, and then after that we'll come back and Daniel will walk us through the last lecture notebook here on boundary terms and convection. All right, thanks.
Yes. What's that? I was at Berkeley. So I was doing my PhD at Berkeley. I was shooting film. Yeah, I think. Well, it kind of seems like at the end of the day, maybe the layers. Got very quick layers and then set it up maybe a bit too thin to be yeah.
The critical layers are narrow.
Yeah.
Yeah.
And we were talking about how, in theory, this seems so easy, like you plug in equations and just kind of go. What exactly makes it really difficult to do?
How to get the setup to try to
That's a good question. I'm not the person to really answer that.
Or like, I don't know if you know why you couldn't just plug Einstein's equations in here and hit go.
So is that spec is the code?
I think now it's like, but
Spec,
yeah.
yeah. So I think they don't have globally smooth solution type. So that is a spectral element, which is sort of confusing, but that sort of means like they take space and split it up into like a few big blocks, and then they do a spectral metric sort of inside each block, and then they link them together. So that's sort of an intermediate between finite element. Really, it's a type of finite element method
Okay.
where they use lots of modes per box. And we sort of use like one giant box with like thousands of modes.
Right. And it's just that the things that you would wanna, that they wanna look at, like the actual problems aren't, not that anything compares to equations.
I think that's right. I think they get like shocks in the.
I mean, the
relative-
original spec, I think, was actually global spectral. So they were only solving the gravity part.
Yeah.
And there, it turns out that, that the solutions stay really smooth.
Yeah, that would.
So they were able to get really accurate solutions. So
Okay, so
Yeah.
it's adding in the MHD stuff that.
Yeah, and that's where you get the shocks.
Would be something.
But it has to do with what you're looking at, not the actual like, method itself.
Yeah, I mean, really, there is a continuum between all the way from finite volume through finite elements, spectral elements, global spectral, right? That is a continuum.
Okay.
People identify with certain parts of the spectrum more or less. But yeah, these things do overlap.
Okay.
So we mostly work on the global case, except, we showed a few examples where you use 2 layers or something.
Right.
So technically, that's a spectral element method. But yeah, basically, when we're at the point of using thousands of modes per box, we care a lot about the sparsity, right? I talked about the randomness and interesting separation. If you're only using 10 polynomials per box, then that's not a big deal. But you just make one system, that's easier. But we spend a lot of time focusing on that, or really going to very high numbers of modes.
This is like an example.
It has to be without shock.
So that would generate.
Try putting the equation. What happened?
So,
I think so.
Yeah. But it would definitely work.
you know how like
Yeah.
it's like
I'm gonna ask what the boundary value thing, because I heard from.
so those
Emma
systems are
that
different, but they all answer.
one of the hardest.
Then I will not have just one
Simulation.
Yeah, for sure. Yeah, and sometimes if you want to do like
You know, it's
very realistic stellar profile or something, you may be better off
So,
like, using Mesa or something to give you the background state and
So
then
then basically
do perturbation. It's not always the best for each of those categories, but sometimes it's.
also just like every over time. Okay.
So you can practice in
I don't think it's not.
one system is just
But, more for solving things.
you make a distribution of that.
What is it, the method exactly? The equation for it?
Making a random.
Just like we can figure out.
Yeah, it's the sparsity, right?
So yeah, what if I just
So when I say
so
implicit,
the first thing I just
so what do we mean?
if you'll be something run all of those different
Yeah, so
systems.
the only thing I think we wanted to differentiate, even for
This is our kind of,
is we
right?
make
So by
a
implicit,
separation.
we use like a first order order of like
So we have 1, 2, 3,
plus 1 minus 0.
I think,
That's the time
check.
derivative.
I think
By implicit, we
one
mean
random number.
here we
like
use
a
X1.
separation. It's like a measure.
So the linear terms are acting on the new state.
Here, two random numbers.
Non-linear terms.
So the system can be like sort of measures equal.
So I can rewrite this as an equation
It'll be like
for X1. So
one,
like
one,
M over
one
GT.
times alpha, one alpha squared is the even separation.
One.
But I think we want like one alpha theta, so that like we can sort of 2 times close together and then so on a bit further apart.
But these alpha.
Or we can multiply off that. So we'll not through like the T.
No, so those are random.
Oh, just run
But, so I think, so to do that, I mean, we could really just do the random.
So now the implicit method is we have to solve this matrix.
Whatever those you should.
Given the current state, we can do everything on the right hand side. Solving the system. So that's hard.
You're interested in
Right. That would scale like n cubed to the size of the matrix, it's totally dense. So if you expand it, then it scales like order.
Where we have different initial mass action.
Yeah, yeah. So
Yes.
In extreme cases, like say,
and
so, quick mass experiments, there will be some simulation
And then usually when they're fully banded, which is often the case, then you can solve the system in order and
so it is sort of
Is
a
it always possible to find the kind of thing?
interpolation problem or.
no, so that does depend
So
on
what
the
if I
PDE.
run like three
But it depends on the separability of the PDE and also the.
No, it's not.
instead of
I'm gonna stay here.
So if you've got coefficients, those can increase the bandwidth here. And then instead of using a direct solve, you might have used iterative solvers.
I guess the thing is,
But in the case,
Dedalus is fine. He's like, if there's some kind of, these words is the best one it can find. And
yeah, so by default, Dedalus will always use a direct solver. But it's also very easy, like the code will just give you these matrices. So if you wanted to run an iterative solver, that's not too hard. You can do that
Yeah.
manually using the matrix extension.
but if it can't find it.
Yeah.
and then we explicitly.
Yeah, so there's like rules for which ones it chooses, or and then for for nice equations, those will always be responses.
Yeah.
But sometimes the equations are just very dense. There's not much you can do.
If I have
So,
a distribution,
Yeah,
initial distribution.
You do what you can.
yeah.
But in general, like you specify the basis.
Yeah,
So-
I guess,
Yeah, so it's like if you make a bad choice.
Once
then
it's
you
better
might-
simulation.
if you make a bad choice, it won't let you correct it.
No.
Sample another.
Well, you specify 5, which is kind of basically beyond.
Oh, did you keep it kind of?
Yeah, but we give up the size.
No?
Yes, no, I mean, that's like,
Okay, did you wanna get solved or something?
yeah.
Yeah, do that.
But it could be that like these are bad, right?
And that,
Maybe do something a little bit different.
yeah.
Like modify these.
So those won't do that. For this choice here.
There's a difference between, I would say, where my career lies.
Okay,
As far as
Yeah, good question. So.
Yeah, I
Remind me
Yeah.
of with all these.
I took that.
Area.
Streaming signal,
Yeah.
I'm trying to formalize that.
Cool.
So this is.
So I do like
Network
Yeah, and it's so, yeah, I just.
And a single
Yeah,
family.
this is the first creator that was.
You're also using it then? Yeah, okay, plus close.
Yeah, it's the, yeah, so it is.
But yon face.
Not academic. We thought about if we could turn.
Yes. Multi-frequency.
That was never.
So we kind of like Oh, okay. Oh, so you're taking a static, you're taking a static model and then doing money. Yes.
Is that right?
Yeah.
I didn't like that. Okay.
I learned this yesterday.
Oh, you are?
Yeah.
Oh, it's very expensive. We don't think we're gonna do that for a while.
That's a great question.
Oh, sure. We do want to get.
Yeah, can I ask one question? So I think this goes back to.
So you evolve the hydro, to some extent stop, do the Monte Carlo,
Yeah.
figure out like, okay, what needs to change, put that back into the hydro.
Yeah.
And then go. Exactly. So not at every time. Yeah. That's what I'll be, so this fall.
That's a good question. We actually separately, we do some combination of the. Of the same.
And that one should be like true.
Yeah.
Yeah, so we'll see how that turns
So I
out.
think what we actually do is something like. GX over.
It's like one semester, it's basically a paper. So I'll be like, effectively the at the low.
I think we do the inverse. I think we do. Exclusively like spring or fall.
You get to pick, so when you apply, you put down your preference for the fall.
Yeah.
They try to make it as accommodation, cause they wanna, I think they take in like.
I don't think
there's
it's
different
clear
things.
that
Definitely
the right
less.
answer to that for this question. Not really.
Yeah, I don't know.
Like for
Right, yeah.
Yeah.
But yeah, you do get to,
format of what.
Really?
I have one more question, but then that's.
I don't know, sorry.
Okay, let's get started. So we're going to skip to lecture 5. This notebook here, and we'll stop with that. So and it's not going to take 2 hours to go through. So if there's any more questions, happy to answer them at the end. So as what Keaton presented, so you can run this notebook on something. You can run it on Colab. You can run it from the cloud. I'm just going to run it locally because if you look, I have like almost no internet for some reason. So a classroom. Okay. Well, I'm just going to do it locally so that and we can deal with that from there. Okay. So the last thing that we wanted to talk about was how to do problems with boundaries. So in Dedalus, when things are periodic, you can use Fourier methods. If you're doing something in spherical geometry, in the angular directions, you can use spherical harmonics or spin-weighted spherical harmonics. But there's some interesting problems that involve boundaries. So for instance, this morning when I was showing these simulations of stellar convection, we want the bottom of the star to be different from the top. So what we're going to do is we're going to do two examples of convection. So that's like when you have some fluid which is heated from below and cooled from the top. So it's going to drive some circulations. And we're going to do two examples of that, one in Cartesian geometry and one in spherical geometry, to give you a sense of kind of how this works. So let's get started. As before, there's various things that are useful for trying to run from the cloud, but I'm going to skip that and just, oops. And then just start from here. Oops. How do I uncomment? Oh, I need to there we go. Okay. So as normal, you start off importing everything. So here I'm loading in Dedalus and everything. Okay. And now in order to impose boundary conditions, we're going to have to do a little bit more mathematics. So that's what I'm going to describe now. The issue is that if we have some PDE, so as Keaton wrote, we have some PDE L U is equal to F. So in Dedalus, we're using the spectral method. We're expanding U in terms of, say, n different basis elements. So we're going to have n degrees of freedom. Okay. And then in order to discretize this continuous in space system, we're going to project out with different test functions. And so we're going to project out with n test functions. And in some cases, those test functions can be the same as the trial functions. In other cases, you want them to be different. Okay? But when you do that, you can think about representing this linear operator as an n by n matrix. Okay, so it's going to be n by n. This is L. Okay, and it's going to be acting on U, which is going to be in a vector of size n. We're going to have F, which is also a vector of size n. Okay, so that's exactly what Keaton was showing up till now. But we have an issue now that we're going to be dealing with problems which have boundaries, which means that we also need to impose boundary conditions. Okay. So in addition to this equation, we're also going to add some boundary conditions. For instance, let's say u goes from 0 to 1. We might want to say that u is 0 on both boundaries. Okay. Okay. And now the issue is that we have two more equations. Okay. Here we had n equations. We have two more here, so that's a total of n plus 2 equations, but we only have n unknowns. So the way that I think about this is that you could, at the bottom of your matrix, add on kind of two rows associated with your boundary conditions. Okay. So kind of like our operator now is no longer square. And the way that we're going to solve this is that we're going to give ourselves 2 more degrees of freedom. Okay. And those we call tau. It'll be a tau 1 and a tau 2. Okay. And those 2 degrees of freedom are going to allow us to satisfy our boundary conditions. Okay. So that's what we're going to set up. Oh, and I guess so then this will be an n plus 2 by n plus 2. Well, we need to add in 2 more rows here. 2 by n plus 2, and then we have our new vector here, and then here we're going to add in the 2 zeros from our boundary conditions, 0, 0. Okay, so then in that case, everything's square, and we can solve the system. That's the idea of the tau method. Okay. So kind of practically speaking, that's how that's kind of what we're going to do. Another way to think about this is that if you have some PD that you want to solve, when we're using boundary conditions, we're going to be using Chebyshev polynomials or using a polynomial expansion. And that means that the solution has to be a polynomial. But the actual solution to the PD might not itself be a polynomial. So in this example, this first order ODE has the solution of e to the x, okay, which is not a polynomial. Okay. If we want to solve this spectrally using bases which consist of polynomials, that means that we cannot represent the exact solution e to the x in terms of polynomials. Okay. So there's just no solution to this differential problem in terms of polynomials. So what we're going to do is that instead of solving this exact equation, we're going to make a new equation which approximates this by adding in kind of one of these tau terms. Okay, so that's what we're writing here. Okay, so we're going to perturb the equation by adding in an extra term here, and that corresponds to these rows, these columns in our matrix. And then we have our extra degree of freedom, tau. So for simple cases, you can solve this exactly. So for instance, in this case, if you take p is equal to x squared, then it turns out that there is a solution u, which is a polynomial. Okay? The polynomial that you get is the second degree, the second order polynomial Taylor expansion of the exponential. So that would be x squared plus 2x plus 2 over 2. Okay? And then you get this extra term here. So this is what we're going to do with our equations. We're going to add in these extra terms, which have extra degrees of freedom. But of course, we really want to solve this equation, right? The solution to this is now a polynomial, so we can't solve it directly. So what we're going to do is that we're going to solve an equation that looks like this for a special choice of p. And then we're going to check to see if this term is small or not. So in this case, the tau is 1/2, which means that that you're not making a great approximation. But if you did this with a larger degree polynomial, then I think that this is going to get smaller and smaller, and you're going to be able to get a better and better approximation to the underlying equation. So in general, there's this issue when you're numerically solving equations that that you're never going to get the exact solution to the equation that you wanted to solve. So you always have two choices. One is you can modify the equation that you're solving such that you can solve it exactly. That's what we're doing here. And then the other case is that you can take the exact solution and get an approximate solution. Excuse me. You can take the exact equation and find an approximate solution to that exact equation. So here we're modifying the equations, and then depending on how you modify it, you're going to get a different solution. But as soon as we put in this modification, it uniquely specifies what the solution is up to like floating point errors. Yeah.
So if you have some nonlinear terms in your boundary condition, then for whatever px you pick.
So those would come over here.
Okay, but so you say that this equation with tau px added, it has a polynomial solution, right?
Mm-hmm.
That's the point of adding that term. Could it be that for whatever p you pick, for certain boundary conditions, you don't get any polynomial solution? Because I imagine it could be, right? If you have some other.
Yeah. So the way that we think about the nonlinear equations is that we think of the nonlinear terms as being kind of absorbed into here. So this operator would kind of tell you like how are things going to change like on the next time step. Okay, and then for this term here, which is going to be a polynomial, this is related to the. I mean, even if it's not a polynomial, this can be calculated based off the state of the system at the current time or in past times. And then once you add in one of these terms like this, that should be enough to make sure that that you have a solution which is a polynomial. Even if this term looks a little bit funky.
Okay, so which of tau and p is the free parameter again? Both or?
So tau is a variable that we're solving for. Okay, the user has to pick what p is.
And how do you pick?
When you change which p you pick, then you're going to get different answers. Okay, and part of the issue is that we're not exactly sure what to pick for this. Okay, we have some rules of thumb, so that's what we're going to talk about. In practice, if you want to do this, what you would do is that you start from an example script which uses a specific choice of p, and you just kind of stick with that. But there are people who are currently trying to come up with algorithms to determine what is the best choice of p to use.
What's the p that gives tau equals 0? That's the goal.
Oh, there is no p that gives tau equals 0. No, normally, if you had a tau equals 0, that would mean that the solution to your equation was actually a polynomial all along, which is rarely the case. Okay. So the question is, how do you pick a p such that tau is as small as possible? Or you could do something, you could ask another question. You could ask, how do I pick p such that I conserve angular momentum? Okay. So you can do that as well. So there's different types of ways that you could optimize what you pick for this. Okay. But overall, we don't mathematically understand why certain ones are better than others yet. This is like an active field of research, and but so for now, we recommend following several rules of thumb that we'll get into in a second. Okay. Yeah. Okay. So I think Keaton's joke about this is that Dedalus is a very Catholic code, right? So all simulation codes must sin, okay? But in Dedalus, we have to confess our sins. We exactly say how we modify the equation so that we can actually solve them.
Who is a god?
So God is the one who came up with the exact solution, right? So e to the x, that's like God here. Okay. Yeah. Or Keaton, it depends on your point of view. Okay. Yeah. So we have a whole page on our documentation talking about more details of this. Okay. Any other questions about kind of the basics of what's going on here? Okay, so we're going to solve a 2D problem now, and it's going to look very similar to what Keaton just presented, but the only hiccup is going to be with these taus. Okay. So let's get started, I guess. Okay, so we're going to do a 2D convection problem. So the way that we're going to do that is that we're going to have a domain which is 4 in the x direction, 1 in the vertical direction. We're going to use the same de-Elixing trick as normal. So first we have to set up the bases that we want for this. So we're going to make 2-dimensional Cartesian coordinates, so x and z. And then in the x direction, we're going to be periodic. So we're going to use a real Fourier series. In the vertical direction, we're going to use Chebyshev polynomials so that we can pose boundary conditions. In particular, we're going to say that at the bottom, you have to be hot. At the top, you have to be cold. And that's what's going to drive the flows. Okay. And now we have to define all of the different fields that we need. So the different variables in this problem are going to be pressure. Pressure is going to be a function of x and z. The temperature, b, so we're calling it b for buoyancy, but think of this as like the temperature. That's also going to be a function of x and z. We're going to have a vector field of a vector valued function u. So it's going to have both an x and a z component. So also a function of x and z. Okay, and now we need to define these tau terms. And the idea is that we're going to be modifying equations like this. Okay. So tau is a variable. When we take a time step, the code will tell us what tau is, and then we could check to make sure that's small. Okay. In practice, we're not going to see what it is, but it's there if you wanted to look at it. And since we're doing a 2-dimensional problem, so in our 2-dimensional problem, we have periodic boundary conditions. We're using Fourier series in x. And then in z, we're using the Chebyshev polynomials, and basically we need to we need to add in a tau for each x position. Okay. So, which is to say that the tau is going to be a function of x, but not a function of z. We're going to be taking our tau. We're going to be adding in terms to our equation. It'll look like this. So we're going to have time derivative of the velocity plus gradient of the pressure. We're going to have a buoyancy term, which is in the vertical direction. We have our nonlinear term. And then we're going to add in a tau term. And the tau is going to be a function of x. And then we're going to multiply by a function, I'll call it p as there, which is a function of z. Okay, so that put together is a function of x and z. Okay? But the tau itself is only a function of x. So that's what we're doing here. It turns out that for this problem, we need these 4 tau terms. There's an extra one that we'll talk about in a minute. And they're all just functions of x alone. Okay. Okay. So here we're defining all of the variables. Okay. Yeah.
Maybe I'll just mention, like, another interpretation of this is sort of that we're adding the taus in as Lagrange multipliers that we use to enforce the boundary conditions, right? The boundary conditions are sort of the extra set of equations we have to enforce. So the taus in the Lagrange multipliers need to have the same number and the same dimensionality as the boundary conditions. So, like, there's 2 buoyancy boundary conditions, top and bottom. Those boundary conditions are functions of x. So the taus are functions of x, and the same thing with velocity. So your taus should always sort of match the structure of your complete set of boundary conditions.
Great, thanks, Keaton. So it's another nice way to think about it. Okay, now, so this block of code, what it's doing is it's just taking some problem parameters and redefining various variables associated with that. So we're defining like x, z, the x and z unit vectors. We have viscosity, thermal diffusivity, and then these terms all have to do with these tau terms. So what this lift does is that it's producing these product terms here. So maybe I'll write it a little bit larger so that you can see. So if you write lift of tau 1, okay, and then you have to give it a basis. Okay, and then you give it this -1. Okay? This is some number n. What that does is that it's going to return tau 1, which in this case is just a function of x. And then you have to pick what do you want to multiply it by. And what it's going to do is that it's going to multiply by the nth elements of this basis. So so what did you call the ultraspherical polynomials? I forgot the notation. C.
C.
Yeah. Okay. So in this case, this would be C1 for the first derivative basis. You can see that we took one derivative of our Chebyshev basis, and then the degree of the polynomial that we're going to use is our resolution -1. So that's what the -1 is. And that's a function of z. So this is our choice of, and this is like that p from above. Okay. It seems like this is a really nice choice that has all sorts of nice numerical properties. that we don't necessarily understand why it's so nice, but it seems to work really well. So this is what I'm saying, that if you're doing something like this, you just kind of keep these things as is. I mean, you could play around and like change these or do something else, but kind of like as a rule of thumb, we kind of find that this works nicely. So the way that we're going to do this is that in our underlying equations, we're going to be using grad u and grad b, which is the gradients of u and the gradient of b, but then we're kind of adding in these extra tau terms in order to make everything work out nicely. Okay. So now we have the equations. Okay. So as before, I'm going to make an initial value problem, list out all the variables. Okay. So the main variables are pressure, buoyancy, and velocity, but then we have to add in all these tau terms. Okay, the equation that we're going to solve, so for buoyancy, it's going to be the time derivative of the buoyancy. This is going to be a diffusion term, so minus the thermal diffusivity times the Laplacian of the buoyancy. So to get the Laplacian, you take the divergence of this thing that we defined up here, which includes tau b1, and you also have to add a tau b2 here. Okay, so that means that we have two tau terms. We can impose two boundary conditions. When you have a Laplacian, it normally requires two boundary conditions. Our first boundary condition is going to be here, that at z equals 0, so that's at the bottom, we're going to say that the buoyancy B, again, think of this as the temperature, is equal to Lz, which is equal to 1. Okay, so we're going to say that the temperature at the bottom is 1. Okay. At the top, when z is equal to 1, we're going to set the buoyancy equal to 0. Okay, saying that the top temperature has to be cold, the bottom temperature has to be hot. Okay. Is there a question?
Oh, we're just going back. It seems like the lowercase lift is something different, and I was just wondering what that was.
Yeah, so this is just like a convenient way of defining these, so that you don't have to every time pick which basis you want to use and which value of n.
Oh, okay. It just uses the one.
Yeah, that's right. So in each of these cases, the arguments are always the same, that we're using this first ultraspherical polynomial and the n-1th polynomial, like degree. Okay, so that's the buoyancy equation, and then we also have a negative, the advective term, negative u dot grad b. So the dot product is the at sign. For the velocity, time derivative of velocity minus the viscosity times the Laplacian of the velocity with these tau corrections, plus gradient of the pressure. This is the buoyancy, gravitational force, saying that the hot things rise, cool things fall. It's only in the vertical direction. So we're multiplying by the unit vector in the vertical direction. We have a tau u1 in here, and then a tau u2 here. That's because, again, we're going to have two boundary conditions. When you have a Laplacian, you get two boundary conditions. These are vector boundary conditions. Tau u1 was a vector field. Okay. u1 and u2 are vector fields. So that means that we need to specify both the x and z components of the velocity. Those are being set at the same time here, that both components of the velocity are 0 at the bottom boundary, and both components of the velocity are 0 at the top boundary. Okay, and then finally we have the advection term, negative u dot grad u. Okay, we're also going to solve we're going to assume that the flow is incompressible. So for incompressible, we're going to take the trace of the gradient of u. That's the same thing as the divergence of u, except that it adds in this tau term here. And the point is that it turns out that it's convenient to have a tau term here, which exactly compensates for a tau term here. Again, this is not completely understood, but just via trial and error, we found that this works out very nicely. Okay. And now there's one last term, this tau p. And what this comes from, this is called this is related to a gauge choice. One way to think about it is that if the divergence of u is 0, so we're trying to solve the equation div u is equal to 0. Okay. So in general you can do this, but the issue is that the code didn't know that on the right hand side that you actually had 0. Okay. You could have put something else there, right? But the issue is that if you take a volume integral of this equation, via the divergence theorem, the volume integral of the left-hand side will be 0 with appropriate boundary conditions. And the issue is that we need to write down an equation that will work for any arbitrary f. And the issue is that if you take the volume integral of f, it's not always going to be 0. I mean, in this case, it is 0 because f is just 0, so the volume integral of 0 is 0. Okay, but in terms of like the linear algebra, the system needs to be well posed even if the volume integral of this was not 0. Okay, so what we've done is that we've added in an extra term here, tau p, to deal with that. Tau p, you can see, under bases, it doesn't have any bases. That means it's just a number. Okay, and the number that it's going to be is that tau p will be equal to the volume integral of f. Okay. Because if you add in the volume integral of f to this equation on the right, okay, then this equation does make sense even if the volume integral of f was not 0, okay, because it cancels from the right and left sides. In our case, f was 0, the volume integral of f is 0, and tau p will always be 0 to machine precision. Okay. But you need to add that in order to make the problem solvable. Okay. So that's an extra degree of freedom, and if you add an extra degree of freedom, that means you need an extra equation in order to make everything square. And the extra equation that we're going to impose is a pressure gauge choice. And the motivation for that is that the pressure is only defined up to a constant. If you add any constant to the pressure, it only appears in this spot in the equation. If you add any constant to it, the gradient of that constant is 0, so it doesn't influence things at all. So the pressure is only defined up to a constant, and we need to specify what that constant is, right? Because otherwise, when you try to solve the equation, it's going to be ill-posed. Yeah. So our choice is that we're going to say that the pressure has to have a volume integral of 0. And this equation, this is just one equation because it's taking the full volume integral. This is just one number, okay? And that's this one equation is associated with this 1 degree of freedom right here. Okay. So again, this is like a little bit technical, but yeah, it's just something that you can just copy and paste. Right. Any questions about that? Okay. So, Okay, so going from the periodic problem to this problem with boundary conditions, it's a little bit annoying because you have to deal with these tau terms. But again, this is something we have lots of examples, and you can just copy and paste from the examples, and that's what we recommend users do. Okay, so after that, everything's going to be easy. So let's look at what else we're going to do. We're going to decide how we're going to do the time stepping. We're going to solve the equations up until t equals 30 using the second order Runge-Kutta time stepper. We're going to set the maximum time step. The next thing is to build the solver. So that's going to make all the linear operator matrices associated with this problem. So in the problem that Keaton showed, because it was just one dimensional, there was just one matrix. Okay. Here, the dimensionality is going to be related to the resolution. So we go up to the top. We're running with 256 Fourier modes. So there should be one matrix per Fourier mode. So there should be 256. Okay. And then the last thing that we're going to do here is pick our initial conditions. What we're going to do is that we're going to first put in random noise, damp the random noise to 0 near the walls, and then add in the linear background. So this is 1 minus z. Recall the boundary condition is that the temperature buoyancy is 1 at the bottom, 0 at the top. So 1 minus z satisfies those boundary conditions. So that's what this linear background is going to be.
I have a question about the time step.
Yeah. Well, actually, first I just want to mention about this. So we said we're going to use 256 Fourier modes, okay? But that's 128 cosine modes and 128 sine modes, and the matrices are the same for the cosine modes and the sine modes. So you can see that we're making 128 matrices. I'm about to talk about the time stepping. So how about I talk about that first, and then you can ask your more detailed question about that. Okay. So next up, we're going to do some analysis. So what we're going to do is that we're going to output files into snapshots_rbc, and every 0.25 time units, we're going to output the buoyancy b, and then we're also going to output the vorticity. So that's the curl of the velocity. Constructing the curl is a little bit tricky here because it's a 2D problem. If you're doing a 3D problem, you could just write d3.curl, would know what the curl is. But it's a little bit more complicated in 2D. So this is the way that we calculate the curl in 2 dimensions. Okay. So every 0.25 time units, it's going to output the buoyancy and the vorticity as a function of both x and z. And then later we're going to take those and make a movie out of them. Okay, next up, so there's a question about time stepping. So I'll just say how we're going to pick our time step sizes, and then I'm happy to answer the question. So we're going to take time steps based off the CFL criterion, and so we have the CFL class that will help us do that. So I'm just going to say a little bit about what each of these numbers are, just so that you have some idea of the different things you can play around with. On the first time step, you like in this case, like we don't have any velocity. Okay, so instead you have to tell it what size time step you want to take on the first time step, and so that's going to be our max time step. So 0.125. Okay, it's going to actually calculate the CFL criterion every 10 time steps. It's going to use a safety factor of 0.5. I think yesterday Mike called this the Courant factor, the Courant number. So more explicitly, what we're going to do is that we're going to take delta t is equal to, we call it safety. And then you take the minimum of 1 over, let's see if I can get the units right. Is it u over delta x?
Yep.
Plus w over delta z, okay, in absolute value. Okay. And this is the minimum over all grid points. Okay. So at every grid point, we have the horizontal velocity u, the vertical velocity w, and we do this. So you can see in one dimension, this would reduce to delta x over u. Okay. But for multiple dimensions, we just kind of add up like this. Okay, and then the safety factor is just like the multiplicative factor that you add in front. Yeah, kind of traditionally it's called the safety factor. So some people think that we should call it the danger factor because the higher it is, the larger the time step is, and the more you're kind of flirting with disaster a little bit. Yeah, so in this case, we're taking a safety factor of 0.5. It turns out that numerically, it's very efficient if you can take multiple time steps all with the same time step size. When you change the time step size, we have to refactor some matrices. So there's some costs associated with that. So we're only going to change the time step if the predicted new time step that we want differs from the old one by more than 5%. If the new time step is the same as the old one to within 5%, we're going to kind of just not worry about that small change and keep on using the old time step size. And then here we're saying that that we'll only change the time step increasing by up to 50% or decreasing by at most 50%, which can kind of help with possible stability issues. And then the maximum time step that we'd ever take is this max time step. Okay, so those are all various parameters. So for me, I often set this to 1, but I guess it's like an extra calculation that you have to do every time step. So it's a trade-off. Yeah.
Does this safety parameter also depends on dimension or something?
No. So here it should not depend on the dimension because we are doing this sum here. Okay. Another way to say that is that if things are isotropic, so like the typical size of u and w are the same and the size of delta x and delta z were the same, then going from 1D to 2D, the denominator here would get larger by a factor of 2, which would mean that kind of the time step sizes that we have to take have to decrease by a factor of 2. But this seems to be a good estimate for when things are stable or not. So when you change dimension, you don't normally change the safety factor. Yeah, but again, right. So I'm writing this down because there are lots of different ways that people calculate these things, and this is what we actually do in Dedalus. Any other questions? I know people love time stepping. Yeah.
So back up above when you set it to 0.125, the max time step, because we're ultimately feeding that back into the CFL criteria, and it was never going to be greater than that. Is the choice of that number to some extent informed by like what cadence we want the output or something, or?
No, so this number just comes from the fact that I know something about, I already know something about this problem. And this is like a reasonable upper limit on the time step for this problem, given everything that I know about it. Yeah. So
So it's like a problem that we're not familiar with, and you probably want to play around with that to some extent.
Absolutely.
Okay.
Yeah. This is a number that, like the max time step size, that's not something that you should copy from like our script to like whatever you want to do, because it could be very different. And so sometimes people do this and then they come up to me and say, Daniel, it's running really slowly. And I say, oh, what's your time step size? And they say, oh, every single time step, it always takes 0.125. And I say, well, like on what time scale are things supposed to be changing? They say, oh, well, like the natural time scale in my system is 1,000,000. And I say, well, maybe you should take larger time steps. And then they change it, and then the code's like 10,000 times faster. So it's something to be aware of.
With the threshold value, is it comparing back to the last?
Yes, the last one.
So
Or
it
sorry.
could move quite a, like, could it move quite a bit just in increments of like 0.5?
Yeah, sorry. Okay, so yeah, so you're going to take a time step of a certain size. Okay, then on the next time step, you calculate with CFL, or in this case, every 10 time steps, you would calculate the CFL criterion. Okay, and then it's going to tell you a time step, and then you're going to compare that with your previous one. Okay, if it's less than 5% of, if the deviation from the previous one is less than 5%, then you use the previous one. Okay. And then after 10 more time steps, you're going to compare, okay, and it's again to the previous time step, but it didn't change from the last time, right? So you're going to have like a long period all with the same time step size. Yeah, and the first time you have a deviation above 5%, that's when it's going to switch. So this is also something that you can play around with, but normally 5% or like 10% is pretty good. And any other questions about the time stepping? Okay, the last thing is the main loop. Okay, so what we're going to do here is, until we hit the stop condition of 30 time units, we're going to calculate the time step using the CFL criterion, take a time step of that size, and then every 100 time steps, it's going to, and I actually don't like 100, I'm going to switch it to 10, I'm a bit impatient. It's going to tell us what iteration it's on, what time it is, and what the time step size is. So let's run that and we'll see if it actually goes. Okay, so there you go. So it is, it's chugging away, and you can see that, oh, maybe, can I do this? Okay, so the first for the first like 100 or so iterations, it took time steps that were the maximum size. Okay, and now it's starting to change the time step size. And what's going on is that this was the linear phase of the instability, and then it starts to become nonlinear. So the advection becomes important, and we have to change the time step size. And you can see that here, I mean, it's changing the time step sizes like every 10 iterations, which is as fast as possible. But then here, all of a sudden, there were like 20 in a row that took one time step. Here it was 30 in a row, 20 in a row. Okay, but now this one, all these were with constant time step. All these are with constant time step. Okay. So it kind of varies this. Okay, so we're at t equals 20, so it's going to go until 30. I guess while it's running, any questions? Questions about anything? What happened? Oh, there was so much output that I collapsed it all into one. Okay, well, I'm bored, so instead of letting this run, I actually ran it while Keaton was talking. So we're just going to load that in. You see, I made this new directory snapshot saved. And this is going to, this is just like a little script that's going to load in the buoyancy and vorticity, and then make plots of this. Okay. And then once it's done running all that, see it's still running. Then we're okay. So now it's done. We're going to see a movie. To make a movie. Okay. So this is our movie. It's going to, so this is our simulation. Goes in X, it has size 4, in Z, it has size 1. At the top, we're going to plot the buoyancy, at the bottom, the vorticity. So the buoyancy, that was set to 1 at the bottom. That was our boundary condition. That's why it's red. And then at the top, it's set to 0. That was the other boundary condition. Okay, so I'm going to play the movie, and you can see that the hot red fluid starts to rise, and then it kind of gets all mixed up. And then at the end, I guess this loops. At the end, we develop these kind of convective rule structures, which is typical for these types of two-dimensional simulations. Okay. If you look at the vorticity, you can see that you start to develop, you develop all these structures at the boundaries. That's because you have these viscous boundary layers associated with our no-slip boundary condition. Yeah, so that's kind of what's going on there. Okay. So this is maybe like a better example of like a more serious calculation than what Keaton was showing, like just the 1D cases. So here we set up the equations, we impose the boundary conditions with all the tau variables. We set up some output to generate as the simulation ran. We're taking time steps using the CFL criterion. We run the simulation. We have a bunch of data that's like in some HDF5 files. We read it in, do some analysis, in this case, visualization, and then look at the result. Okay. Any questions about all that? Okay, if not, I just want to finish up by talking about how to do something very similar, but now in spherical geometry. Okay. So we're going to talk about a similar system, but now it's going to be three-dimensional. We're going to have a spherical shell. It's going to be a narrow shell. The bottom will be at a hot temperature, and the top will be kept at a cold temperature. Okay. So this is maybe modeling a bit about what's going on, like in say in like these surface convection zones in massive stars, where you have like a little convective layer at the surface, where effectively at the bottom it's being kept at some hotter temperature, and at the top it's at some colder temperature. So you're driving some circulation cells. Okay, so the way that you do that in Dedalus is that you, so here we're just going to define our different parameters. This is the inner radius, outer radius. So we've non-dimensionalized the problem, so the width of the shell is going to be 1. Then it's going to be in spherical geometry, so we're going to have 3 variables, phi, theta, and r. The phi resolution is going to be 128. The theta resolution will be 64. The radial resolution, we're only going to use 8. Not much is going to happen in the radial direction. Specified the radii as being of the inner radius as 14 and the outer radius of 15. And then as before, we're going to define our variables. And it's the exact same variables as before: pressure, buoyancy, velocity. And then the taus are the same as before. The only difference is that the pressure, buoyancy, velocity, those depend on, those are defined over the shell basis, which is which depends on phi, theta, and r. And then our tau terms, those only depend on theta and phi. So that's this sphere. Okay, so these are the same types of parameters that we that we used before. Now we have a radial direction instead of a vertical direction. Going to use, again, this so-called first order reduction. Then for the equations themselves, these are almost exactly the same equations as above. The only difference is that we switched from the boundary conditions now are at the inner radius and outer radius, whereas above the boundary conditions were at z equals 0 and z equals 1. Okay. But otherwise, these equations here are the exact same. And this is actually something important to point out, because if you were to write out the equations in components, like in terms of like r, theta, and phi, these would be a huge mess. Because if you've ever looked up on Wikipedia what the Laplacian is in spherical geometry, there's a huge spray of terms. Okay, but in Dedalus, that is all taken care of automatically right here. Okay.
Also, I think you said it takes care of the singularities in the coordinate system.
It takes care of all those geometric factors. So you can write down the equations all in terms of vector calculus operators. Okay. And it'll do all the right things for you. So in general, kind of like one of the things that's cool about Dedalus is that you can do different types of geometries. Like this morning, I talked about Cartesian simulations and spherical simulations, and it's all the exact same code. It's just you just change like a few things. I mean, yeah. So going from Cartesian to spherical, it's going to be changing like basically like 10 lines of code. Okay, just kind of like where you impose the boundaries. A few things about like the coordinates, stuff like that. So that's kind of the power of the flexibility of Dedalus. Okay, it's complaining because I never ran this, I think. Oh, and I didn't run this either. I just haven't run anything. Okay, let's start from there, I guess. Okay. So as before, we're going to set our stop condition. Pick the time stepper. This one's a multi-step time stepper. Max time step size. So before it was less than 1, now it's 1. The problem set has changed a little bit. We're going to build the solver, build all those matrices. In this case, in spherical geometry, you have a different matrix for every L, but the matrices are the same over M. If you think about spherical harmonics, azimuthal wave numbers M and spherical harmonic degree L. And then the initial condition is going to be set in the same way as above. So now you can see it's making all these matrices. Okay. Next thing. So while that runs, I'll just talk about these. So we're going to output some more complicated things. This is a 3D simulation, and the problem with 3D simulations is that they generate a lot of data. You probably don't want to output the full 3-dimensional data very often. So here, what we're going to do is that we're going to output the temperature, like buoyancy, at 1 radius. So kind of like the midpoint, halfway between the inner and outer radius. So that's how you do that, like this. Okay. The other thing that we're going to do is we're going to calculate the buoyancy flux. So that's the radial component of the negative diffusivity times the buoyancy gradient. So this would be the diffusive flux, and then this would be the advective flux. And we're going to output that at the outer radius, inner radius at phi equals 0. So that's on like some meridional slice. Then at phi equals 3 pi over 2. So that's another meridional slice. And these are actually going to get stitched together to make some sort of like 3D visualization. Okay. For CFL, it's going to be similar to before. our safety factor here is 2. Okay. So that means that we're going to take time steps that are longer than the time it takes for the signal to like propagate over a single grid cell. So it'll like propagate over 2 grid cells. And it turns out that that works out just fine. Okay. So on spectral codes, sometimes you can take time steps that are larger than you would expect from the CFL condition. That is the case here. Yeah.
So yesterday we saw that fail catastrophically for finite difference. Is this like a feature of spectral codes that you can take longer time steps?
All right. So there's 2 aspects to this. You can take longer time steps for a couple of different reasons. One possible reason is that if you remember when you talked about these Chebyshev grids, they kind of cluster near the boundaries. If you have flow through the boundary, it turns out that you can jump over multiple grid cells, like as many as like 10, 20, 50 grid cells in one time step, and that's fine. Okay? So that's a property of the spectral method. The reason why we can do it here isn't because of this, because in this case, if we look at our boundary conditions, was that the velocities were 0, so that means that there's no flow through the boundaries. So the case that I just described isn't happening in this simulation. The reason why we can take large time steps here is because of the because it turns out that the solution is going to be pretty diffusive, and the viscous terms are going to kind of help out and stabilize us. So that's the reason why we can take large time steps here. Okay. But otherwise, it's pretty similar. Okay. And then this is so this is the main loop. It's going to look very similar to the one above. And okay, and now I'm not going to actually run this simulation because my computer is really slow. So it'd be kind of boring. So instead, what I've done is I just downloaded off the website. Keaton put up a video of what the simulation looks like. So I'm just going to try to load that in here. Okay. So this is going to be the result of the simulation. Okay. So not too much is going on here. It's not turbulent for sure. So this is actually convection in a specific regime called spiral defect chaos. You can see that there's kind of these spiraling patterns which merge and shift over time. Okay? So there's lots of like laboratory experiments of stuff like this in Cartesian geometry. It's hard to do laboratory experiments like this in spherical geometry. But it's kind of fun to do in spherical geometry because there's like some topological issues differences between a sphere and like a square. But this is like kind of what the simulation looks like. Okay. So to go from this to kind of like the types of simulations I was describing this morning, that like get into papers, it's really very similar scripts. It's just that they are kind of the diffusivities are much lower, the resolution is higher, and then they're run in parallel. But as Keaton was describing, to run this in parallel actually doesn't you don't change any of the scripts at all. The only thing that it only changes in one spot, which is up here in the mesh. If you're doing a 2-dimensional problem like this, you can pick the domain decomposition. If you remember this morning, Keaton was talking about how in the spectral space that you can have different cores having only a few of the kx's and a few of the ky's, but it'll have all of the Chebyshev coefficients one core. So you get to pick, say if you had like 1028 cores, how do you want to distribute across the kx's? How do you want to distribute across the ky's? So the standard thing to do would be to do 32, 32, so something that's even. So that's saying that, or I guess in this case we have phi's and thetas, so it'd be like 4 in the phi direction and 2 in the theta direction per core. Okay, and then each core would have all 8 radial coefficients. Okay, this is a pretty small simulation. You wouldn't want to run it on 1,000 cores. A lot of the time would be spent doing parallel communication. But if you kind of increased all these by a factor of 8 or so, so I don't know, go more like this. This is then becoming like a more serious simulation that you would have no problems running this on like 1,000 cores. Yeah.
Is there like a maximum mesh block size that you recommend? Like 32 is probably safe.
I always do it isotropic. I have done tests where instead of doing this, I do like 64 and 16, and the performance is pretty similar. If you did like 2 and 512, well, then you actually come up with an issue here. I guess maybe this is pretty high resolution, but if you did something that's isotropic like this, you wouldn't be able to run a simulation of this size on that, because if you're splitting up the phi's amongst 512 cores, well, there's only 256 different phi's, so some of the cores are just not going to do anything, right? So for a case like this, that's exactly why kind of 32 is going to work nicely. Yeah, and I guess I should say that like the spherical simulations I was showing at the end this morning, those were kind of run on a grid with like this type of resolution. Okay, so it was like 1024 degrees of freedom across the convection zone, and then that was being run on, I think, 16,000 cores. So that was multiply each of these by 4, get 128 by 128. Okay. So you can do this on like pretty large problems, and the scaling is pretty good. Okay. So I think that's all that I had to say about this notebook. Any other questions about the notebook? Okay, and I think that's all that we had to say about Dedalus. So any last minute questions about Dedalus? Yeah?
Is the code made to make this spherical visualization public or in the notebook, or is that?
It's not in this notebook, right? But let's see. I'll see how my typing is without looking at anything, or how the internet connection is. No internet. Okay. Someone said I'm supposed to join the classroom.
Yeah.
What's the password? Is that right?
Yeah.
Okay. So we have these. So that last example is one of the examples that we have in the main code base. So all this is like on GitHub. So this is the problem, and you can see that that here we recommend to run on, say, like 4 processors, and says it should take about 20 CPU minutes. So on 4 processors, it'll take about 5 minutes to run. And then afterwards, you can make a bunch of snapshots using this script plotshell.py, which is like in the Dedalus main repository, GitHub repository. So that does the 3D visualization. So if you're curious, you could take a look at that.
So I just confused on the timestamp choice. So it seems like you just test the timestamp and maybe make the choice. Because you previously also mentioning the cache instability, if you choose smaller timestamp, you tend to get higher resolution. So there is just no standard that you could rely on, so just keep testing.
Yeah, that's right. So how do you pick the time step size? I mean, normally we're doing this based off the safety factor, and normally what I do is that just kind of like look at some of these example problems and pick a safety factor based off that. Those are normally pretty safe. If you go to smaller time steps, you're going to get higher accuracy, but it'll take more time to get the answer. Here we're setting the time step size not based off accuracy, but instead on stability. So we kind of want to know what's the largest size time steps we can take and still maintain a stable integration.
Okay.
For other types of problems, you're more interested in accuracy. In that case, you might want to take time steps that are much smaller than what is required for stability. So it kind of depends on the use case. But yeah, in general, I would say, yeah. So actually, for that reason, for different use cases, for different problems, you should want to use different time step size. So if anyone tells you this is the time step size you should pick, I think that they're wrong.
So for example, if I want to get more accurate results, so I can either choose more basis or decrease time step. So how do I make the choice? I just test. That's all.
That's right. Yeah. So I mean, the most straightforward way to do this is to increase the spatial resolution, increase the temporal resolution, aka decrease the safety factor, take smaller time steps, and see how those things independently and together influence the solution.